Welcome to 6502 Assembly Language Programming. In this video, we'll write our first lines of code. But before we can write any code, I need to introduce you to the 6502 microprocessor. It is an 8-bit microprocessor, which means it handles 8 bits of data at a time. It has 3 general purpose registers, all 8 bits, an 8-bit stack pointer, a 16-bit program counter, and a program status register. It supports 56 instructions and can address up to 64 KB of memory. Here is a block diagram of the 6502 microprocessor. On the left is a depiction of the register file. Just going through the registers in turn, the A register or accumulator is the target or the source of data for most arithmetic operations. The X and Y registers have a limited arithmetic capability but are used for advanced memory addressing. The PSR or program status register contains information about the last arithmetic operation performed. It answers questions like, was the result 0? Was the result negative? Was there an arithmetic overflow? That sort of thing. The stack pointer indexes the stack area and is used to contain temporary variables, but most importantly, the return address of the last subroutine call. You'll learn about subroutine calls later on. The PC, or program counter, is the only 16-bit register, and it points to the next instruction to be executed. On the right of the diagram, you see a depiction of the address range of the microprocessor. At the very bottom, or top, depending on how you look at it, of the address range is the base page. Addresses 0 through FF hexadecimal or 256 decimal. This area is very important because when you put variables there, you can address them with only an 8-bit address. This area is heavily used because of that efficiency. The rest of the address space, must be addressed with a 16-bit address. And this makes instructions that do that 8 bits longer because they have to have a 16-bit address encoded. Now, the 16-bit address bus is the mechanism that communicates the address of data to be manipulated. And the 8-bit data bus is where the data is transferred to and from memory or from the CPU to and from I/O devices. This course is about assembly language programming, and the assembler we use in this course is DASM.js. This is a depiction of the DASM.js operation. It reads the source code, featured on the left, and produces 2 principal outputs, the object code and the listing. The object code will actually run inside of the browser using the Java Tari simulator, and the listing will be displayed for you to refer to. So let's get started. You want to go to the course code at the link on the slide that you'll also find in the description, and you can click on it there. Once the web page loads up, click on Solve the Exercises. Let's learn how to use the 8 bits and 1 byte tools so that you can write and run our first lines of code. To begin with, Let's navigate to the 8 bits and 1 byte IDE. Click on the link in the description labeled Course Source Files. Once you are here, then click Solve the Exercises. Now, once you have saved your work, you can navigate directly to the playatari.html web page, and there's a link to that in the description as well. Here we are at the 8 bits and 1 byte IDE. It consists of a source tab where you write your code, a run tab where you execute and debug your code, and a files tab where you can save your work and then load it later on. The source tab consists of the in-browser editor and the pull-down menu. The in-browser editor is powered by CodeMirror and provides a usable, if basic, code editor. We're going to click on the pull-down menu to select ex0.asm. This file that was selected is not on your hard disk, but in a virtual file system within the browser. But do remember you can save your work with the Files tab. The course includes 12 exercises which are associated with source files named ex0 to ex11.asm. Note that when viewing one of these source files, the Source tab displays a button labeled See Solution. If you click on that button, it will overwrite your source code with My Solution. After you've coded your solution to an exercise, click on the Run tab to test or debug your solution. I want to explain a few things before moving on to the Run tab. Our program is built from a number of separate files. The principal one is course.asm. So let's look at that. Course.asm includes all of the exercises and defines the variables used in the exercises. Let's walk through it. At the beginning of course.asm, you see the processor directive. That just tells the assembler what exact language we're using, since it supports a number of microprocessors. Moving on, list off suppresses the following lines from being included in the listing until the assembler sees list on. All the subsequent lines are included in the listing. This segu indicates an uninitialized segment of memory. The assembler may define this memory in terms of assigning labels to addresses, but it will not define the contents of the memory. Moving on down, org hex 80 indicates to the assembler that the next label should be assigned to the address 80. And looking at the first label, param0, you can see that we've defined 1 byte to be assigned to that. That means the assembler will allocate 1 byte of storage, and so that the next label will be assigned to hex 81. Moving down further, here at line 92 we have seg code. Since it's not seg.u, we know we're actually going to define the contents of memory here, and it's going to start at address hexadecimal F000. In the Atari 2600, the code existed in ROM, which was in high memory starting at that address, and the RAM was in low memory starting at address 80. The following includes bring in all the exercises into the course.asm assembly. Now I've separated these out so that when we look at one, that we don't have to deal with all the code around it. We'll just see the code of our exercise. Okay, well, let's move on to the Run tab. So the things I want to point out here are, one, the semicolon, which is the introduction of a comment. Every line starting with a semicolon is a comment. The assembler ignores the content of these lines, and so you're free to write anything you want here in terms of documentation or whatever you might think you want to know later. And here I'm using it to communicate the requirements for a successful completion of this exercise. Now, the exercises, each exercise is a subroutine. A subroutine is a named sequence of instructions that can be called repeatedly, but is also useful for isolating that sequence of instructions so that you can code them in isolation without having to worry about surrounding instructions. Now I want to talk about the protocol for solving an exercise. Having read the instructions, you'll code your solution and then change this LDX # not implemented to LDX # implemented. Now, since we're talking about LDX, I need to tell you what that is. That stands for load X, and it transfers data from memory into the X register. Let's use our instruction reference to find out about the LDX instruction. Now, I have provided a link to this web page in the description below. It's an excellent instruction reference for the 6502 and rather better than the other ones out there, I think. So, at the top of the page here, we have a list of the 6502 instructions. We're going to click on LDX. As you can see, there's quite a bit of information about the LDX instruction. It tells you what it does, loads a byte of memory into the X register, and it tells you how it affects the flags. The flags are individual bits in the PSR that we've talked about before. In this case, it sets or affects the 0 flag and the negative flag. And these flags are either set to 1 or 0, depending on whether or not the result is 0 or the result is a negative. Below that, we have the addressing modes that the LDX supports. Now, the first two are the ones that are of most interest to us. Immediate means that the memory address being loaded from is in the instruction itself, and that's appropriate when you're loading a fixed value, a constant value that is 8 bits or less in terms of its width. So loading, in other words, something that fits into a byte. The other form of addressing that's important to us is zero page addressing. Now, zero page is addressing in the first 100 hex bytes of storage, from 0 hex to FF hex. This area of memory can be addressed by 1 byte. So this makes for very compact instructions. So the zero page form of LDX is 2 bytes long, quite compact, and requires 3 cycles. Now, a cycle is short for clock cycle, and clock cycles are the heartbeat of a microprocessor. They determine how fast things get done and when they get done. Alright, so we've looked at LDX. Let's look at the other load instructions. The next one to look at is LDY. LDY is virtually identical to LDX, except that it loads the data into the Y register, not the X register. Let's have a look at LDA. LDA is similar in that it loads a byte of memory from storage, from memory that is, into the A register. It sets the flags in the same way as LDX. However, it does offer more addressing modes. While we're here, let's also look at the store instructions. We'll look at store A. This transfers information from the A register into memory. And store X and store Y does the same thing, but with the X and Y registers. Let's have a look at the Run tab, and then we'll finally get around to writing some code. The Run tab consists of a listening pane here, a debug pane here, and the simulator pane here. The listening pane consists of the listing, which is produced by the assembler, and then this border over here, perhaps you could call it a gutter, with these line numbers. The principal reason for the border is so that you can set breakpoints. Now by clicking on line 7.7, I put a breakpoint there. That stopped execution at that point. I'm going to remove that breakpoint by clicking on it again and click resume. So the main features of the listing are that in the left-hand column you'll find addresses. If the address has a U in front of it, that represents uninitialized memory. So even though here at line 41 it has zeros here, as if it was reserving zeros for that spot, it's just declaring an address 80, and it's telling you that param 0, which is 1 byte, is at address 80. Param 1, which is 1 byte, is at address 81, and so on. Let's look at some code. Looking at EX0, you see that's at address F000, all numbers hexadecimal, and we are generating some code at that address. We have the LDX instruction, and that is what this code here means. It means LDX hashtag not implemented. The 60 is the return from subroutine instruction. Return from subroutine instruction, excuse me. Mainly the listing is a tool for you while you're debugging the code, because you'll need to know the exact address of what everything is at, and yeah. So going to the right, you have the debug pane. The debug pane consists of this text area, some buttons at the top. You have a zoom in, a zoom out, a log pane, and that's what this is. It's a general area for information, and the assembler can put information here. These lines here are from the assembler, and the debugger can put information here. So it's a bit of a catch-all. Here the debugger, when it was in break state, dumped the contents of memory. Remember, the Atari 2600 only has 128 bytes of RAM, and these are them. It has a lot more in ROM, or simulated ROM I should say, but that doesn't change. That is this. That will not change during execution. The debugger also puts the CPU registers over here in the log pane, but there is another view of the registers in the CPU pane, and this is presenting the same information about the registers, except that you can, for instance, change the base. Oh, if you're in break state, you can change the base. Let's get in break state. You see we're in base 10. Now it's base 16. Now it's back to binary, base 2. And note that you can only change the base for the general purpose registers. I didn't see any point in changing the base of the stack pointer or program counter or the PSR, because you're always interested in the individual bits with the PSR. The other thing you can do on this pane is click on header, and it'll remove the column headers if you find that more readable. And down at the bottom we have the Atari 2600 simulator. I'm going to remove this breakpoint and resume with its display screen and the simulated Atari console. These buttons are all operational. The code that's running may not listen to them. It doesn't matter if they listen to the off button, it still gets turned off. But if you turn it on again, the code will start running again. Okay, I think we're ready to write some code. Let's go back to the source pane and look at our exercise. It has some introductory information here about subroutines, and then here is our assignment. The X0 accepts one parameter which is passed in param 0, and its job is to copy that value to output 0. Having done that, it should set the X register to implement it, to tell the caller, which is the test code, the exercise evaluation code, that we've solved or attempted to solve the exercise. Alright, so we've learned about load and store instructions, so we're going to use those. And it's fine if you want to pause me and solve this yourself. I'm pretty confident that you can do it, so I'll give you a moment. Well, welcome back, or thanks for staying, whatever is the case. Let's solve this puppy. So we're going to load param underscore 0 and store it in output underscore 0. And we're going to set this to implemented. Okay, let's go to the run pane. And down here, I don't think I've explained this yet, but you're going to see this screen throughout the course. And basically, every time you solve an exercise, you get a light changed from red to green, from yellow to green. If you get the exercise wrong, you'll see a red light here. For instance, let's go back to the source code, and let's code a bug and click run. Okay, so now you see this light turn to red. Going back to the source, we loaded param 0 into A, but then we stored output 0 from X, so that's not going to work. So we could fix it by changing this to LDX. And so we're loading param 0 into X and then storing X in output 0. That'll work. So we click run, and that works. You do the same thing with Y. We'll do Y too, just to be complete. Yay. Now I want to demonstrate some things with the debugger. So I'm going to go find our code. And here it is. And put a breakpoint there. So you see we're doing, this is our code where we did the LDY and the SDY. But I want to demo these buttons here. Now resume just means to resume execution. Doesn't do much. If you leave this breakpoint here, it'll just circle back to the breakpoint and stop again. If you get rid of the breakpoint and click resume, then the code will run. But let's put the breakpoint back in, and I want to demonstrate these buttons here. Step over means to execute one instruction. However, if you're stepping over a subroutine call, step over will step to the next line after the subroutine call. In other words, it'll allow the subroutine to be executed and then stop execution when the subroutine returns. And in saying that, I realize I haven't really explained subroutines, but I'm going to show you in just a moment. Step into will step into a subroutine rather than stepping over it. It'll step into the subroutine, and we'll demonstrate that in a second. And step out does the reverse. If you're inside a subroutine, it'll step out to the caller. And so what we're going to do is click step out, and here we're in this instruction that's immediately after this jump to subroutine of EX0. And so we're going to click here, set another breakpoint, and resume. And here, if we step into, click step into, it'll step into EX0. And you can do step over, step over, step over, step over, and we're back here again. Let's resume again. And we'll do, if we do step over, it won't go into EX0, it'll just go to the next instruction again. Oh, wait, unless there's a breakpoint. Okay, let's try that again. If we do step over, it'll just go to the next instruction. Now, one thing I haven't explained about Atari 2600 programs is essentially every program is a big loop. It's just going through the same thing over and over again, hitting the same code. What will change is the variables for each loop. But if you set a breakpoint, in the loop, every time it goes through that loop, it's going to hit that breakpoint again. Okay, so I think we've hit how these buttons work. I hope you understand that. I think I'm going to call it an end for the video here. It's gone really long, and I'm sorry, but there's been a lot of information to cover. I hope you enjoyed this. If you've learned something or derived some benefit from this video, please click like and subscribe. Thanks very much, and have a great day.